All right, everybody, welcome back. This is going to be velocity graphs part 2. Let's begin. All right, so the first thing that I want to do with this set of notes is actually go back to velocity graphs part 1 and just do a quick little catch-up of the previous video. Once again, if you haven't watched that video, make sure you do. So from the video, we're going to use the perfect set of data where we got x is equal to 3t squared. We also said that x is directly proportional to t squared. And we also said that using this model, our constant is going to be 3 meters per second squared. Now this is very important, so I'm going to put a little star or highlight that because we will come back to that later. And probably the most important thing is the law. So this is the law of falling bodies. Okay, and that's just a really fancy way of saying the law of objects speeding up. Okay. Now, from there, we created a graph where we got a position versus time graph. Now, if you're wondering, Mr. Lee, should I have all the details that you do? And the answer is yes, it's good habits. And if you have good habits now, you won't lose points for it later. And we created a graph that looked something like this, right? A very parabolic one. All right, and one of the very last things that we did in that video is I instructed you on how to create the tangent lines. And one of the things I told you at the end of the previous video is you need to be able to create 2 tangent lines to show whether this object is speeding up or slowing down. So I will do that. And this is where if you have multiple different color pens or pencils, it really does help. So I'm going to create a tangent line there, like so. We'll call this V1, and I'll do one up here, and we can call this V2, right? And it always does help to have a little statement that is explaining what's going on, and we can say that V1 is less than V2, and we know that because just of the slopiness, right? V1 is more flat, V2 is more vertical, and we can say therefore object is speeding up. All right, now these are all great parts of coming up with your explanation for exactly what is happening. All right, now from there, what we can do is, you see how we did V1s and V2s, right? We could actually do this for all of the data points along that curve. And if we were to do that, we would get the following data points, okay? We would be able to get a data point for velocity and a data point for time, okay? Because we know the tangent line at that time point, at that instantaneous time, which is our t value here, gives us a tangent line, which gives us the velocity. So you know what? I'm going to write that on top. This is the tangent slope, and this is the x value, right? Or the x point. Let's write that as point, not value. This is the x point. All right, as in the x-axis point. So for the time point, we can have a tangent slope, and that slope is the instantaneous velocity. All right, now if we did that with the perfect data set that I gave you from above, we should have gotten the following, right? So for, let's just do for 0, 1, 2, 3, 4. Actually, you know what we'll do? We'll actually pull it right up. Let's take a look at the different point values. Let's do the first one for 0, all right? Now, at point 0, we can see that the slope is obviously 0. So now, let's increase this to 1. All right. There we go. At 1 second, where's the value? Here we go. At 1 second, the value we can see right there, it is 6. So we'll write 0, 6. Now let's increase this to 2. I think I'll just plug it in. There we go. At 2, we can see all the way in the top where it says 2-12. So that would be 12. And let's do that for 3 seconds. Okay. And at 3 seconds, it's kind of hard to see because it's all the way up there. There we go. At 3 seconds, we have a velocity of 18. And let's do the final one at 4 seconds. All right, at 4 seconds, it's really, really slopey. So we'll have to definitely find it. It's kind of hard to see. but it does say, you gotta choose to believe me. Oh, there we go. It does say 24. All right. Now that we have the velocity time data table based off of the tangent lines, what we can do is create a velocity time graph, right? So let's just create a quick little sketch. Remember, for sketches, we don't have to actually plot points, but we do need the general shape. And if we were to plot it, we would get something like this. Okay, now I want to make a little detour. I want to showcase something that's going on here on the table. Notice that the interval between each of these is 6. Okay, coincidence? I think not, and we will see that pop up. Now, when we created this this graph, we found that the slope for this velocity time graph gave us a value of 6. Now, what about the units? All right, so the units is just rise over run. So the units for a rise is meters per second divided by the units for the run, which is seconds. All right, now one of the important things about this slope, and you'll often hear me describe the slope using this method or these units, is that this actually tells us something, right? So if we were to verbalize this slope, we would say for every 1 second, the speed or the velocity of the car increases or changes by 6 meters per second. All right, now that's fantastic, right? That's exactly what the slope tells us. Okay, so for every 1 second, the velocity changes by 6 meters per second. Now, this is important because if you actually take a look at the units, if we do meters per second, what we actually get is 6 meters per second squared. But this doesn't make sense, right? The idea of meters per second squared verbally does not make sense. If you remember from the previous video, right, we said for every 1 second squared, the car moves 6 meters. And I asked you to think about it, and I said, what the heck does a second, what is a second squared, right? What does that even mean? It doesn't mean anything to us. But we can actually count on our fingers, all right, for every 1 second. So 1 second, the speed of the car increases by 6, right? So 1 second passes by, 6. 2 seconds passes by, 12. 3 seconds passes by, 18. 4 seconds passes by, 24. And that's how we actually got this table. And that's why it's so important to know where these units come from, because they actually tell you so much more than you realize. Okay, and so from here on out, you may hear me say or call the units for this as meters per second squared, or you may hear me call it meters per second. All right. Now, with all of this, right, we are coming across our very next definition. So the slope for a velocity time graph. All right, time for the definition. The slope for the velocity time graph is the change in velocity over the change in time. Okay, and yes, I am writing it out for a reason so that you actually have the definition. And if we were to write this out in variable form, we could write it as delta v, because that's a change in velocity, over delta t, which is the change in time. And we're going to give that definition a variable. This is what we call acceleration. Okay, so let's box that up, start that up. That's our definition for acceleration. Now, if I were to ask you in simple terms, right, what is the definition for acceleration? You could simply say it's a change in velocity over a change in time. But what I also like to think about is the object speeds up or slows down. Okay, so this is your evidence. This is your evidence that acceleration exists. Now, if you're thinking, where have we seen this before? I'm glad you're asking, because we've been doing it when we drew our tangential lines. Notice here, V1, the slope is not very slopey. V2 is very slopey, it's very vertical. Okay, our velocity has changed. We sped up, and that is why it is so important to have these verbals down, because within that verbal, right, we have a little clue that acceleration exists. We have stated that the object is speeding up. Therefore, we can say the object is accelerating. So we could actually write this as, because V1 is less than V2, the object is accelerating. Oh wow, we definitely sound like physicists now. Cool. All right, the very last thing that I want to do, if you remember, I told us to keep this k value in mind, and we're actually going to go back to that k value. Okay. If you remember from this graph, right, we found that the relationship is k, or directly proportional to t squared, right? And from the graph that we just discovered, our velocity time graph, we can now come up with another relationship. We know that the slope we can now call the acceleration, okay? And the definition is going to be velocity over time. Now, if we were to come up with a mathematical representation for this linear line, we can use the point slope formula, where it's y is equal to mx plus b, okay? And our y-intercept in this case is just 0, so I'm going to cross that out. Our y-axis is velocity, our slope is equal to the acceleration, and our x-axis is equal to time. All right, so we have this representation here, and we have this representation here. We can also do a quick little scrolling back. Now, if you've been noticing, right, these two values, the 3 meters per second squared and the 6 meters per second squared, right? I highlighted the 3 and I highlighted the 6. So here's something important. This graph, okay, the xt graph, okay, and the vt graph is for the same lab. Okay, this is very important because if you remember from the previous video, we said the xt graph and the xt squared graph, right? We found that the equations or the formulas were the same. In fact, the formula was x is equal to 3t squared, right? This formula was the same for both graphs. It was the same. Now what we're trying to do is we're trying to connect the formula that we got, or the mathematical relationship, x is equal to 3t squared, to this vt graph. And the important thing here is that we found that the slope for this graph was equal to 6. So let's come up with a mathematical relationship between this 3 and this 6. And the mathematical relationship is actually quite simple. We call this 3 the k, so we will say that k, aka the 3, is equal to 1/2 of a. So if you're wondering where are we getting these letters, remember we call this 3 the constant, and we call that constant the k value, and the slope is the acceleration, which we just defined as a. Okay, so our k value is equal to 1/2 of the a value. Now, with that, we can actually come up with one of our very, very, very first equations for an object that is speeding up. And this is an equation that we will find on the formula sheet. So ta-da, we finally made it to the formula sheet. We can say that velocity, or excuse me, we can say that position is equal to, okay, so the k value, I'm substituting in k in for 3, 1/2 a t squared. So if you're wondering, Mr. Lee, where did you do that? Where did you get that? All I did is I substitute in this formula in for k, because our k won't always be 3, right? Our k could be any number, but luckily with this formula, okay, and this definition here, we now have something a little bit more concrete, where we can use this for anything that comes up in the future. All right, wonderful. See you next time. Bye bye.